All right, let's see if I can get a copy of that. Good. Okay. Let's see here. All right. Okay. All right. So did you get your qual exam scheduled yet?
Yeah, I have also the faculty.
Uh-huh.
But no, actually he wanted to what is brief description of research. Research. Yeah. I think it's a new thing.
Yeah. No, I think that's to pick the right people. I'm pretty sure.
Exactly.
I think I got you on or you got me on your committee. Maybe don't tell anybody yet, but which is good. I don't know who else though. Hello.
I don't know when it's gonna be.
Yeah, not sure either. Chalfan, how are you? How's it going? All right. time is it? Where's everybody today? Oh my. Okay, guys, let's go ahead and get started. All right, so welcome back, I guess. Did you guys all get a chance to watch the lecture last time, right? Okay, let me know if you have any questions. Also, I had some questions on the homework, plotting the Druid model. If you have trouble with that, email me or come by office hours today, and I'll be able to take a look at how you're doing it, the mathematics involved and the code that you're writing. One error that I did notice is when you're plotting the Druid model for silver and you use the parameters for silver, silver's plasma frequency is way out in like the invisible range around there, right? So you need to plot on your x-axis at least out that far to see it go through the 0 point, right? So to see the full features that you would see in the slides, you need to plot very far out on your x-axis. So keep that in mind. Okay, very good. Is there any questions on the last lecture that you guys watched or on the homework? I guess we can handle the homework. If you have a quick question, we can take it now. Everybody's doing okay with it? Good, very nice.
Do you have more information about the Cauchy's Mossadi?
The what now?
The Mossadi expression.
Oh, Clausius-Mazzotti. Yeah, definitely. Clausius-Mazzotti. So today we are we saw Clausius-Mazzotti in the last lecture, right? There's another formula called Maxwell-Garnett that happens after Clausius-Mazzotti. Clausius-Mazzotti is it's a mixing formula to find the effective permittivity of a medium made with metallic spheres, right? But then if you want to use dielectric spheres rather than metallic spheres, then you can also derive a similar equation called the Maxwell-Garnett mixing formula. But that's in the notes. We're going to skip that, and we're going to move on to the wave equation and solutions. But if you have any more information, or if you're more interested in that, let me know, and I can give you more information. Yeah. Okay, good. All right, let's get going. So we are on lecture 3 now, wave equation and solutions. We're now going to solve for what the wave equation or what the wave functions look like that are solutions to the wave equation. We're going to solve it in 3 coordinate systems: rectangular, cylindrical, and spherical. These are 3 common coordinate systems used in electromagnetic theory. Of course, we know how to handle it in other coordinate systems, at least integration and vector calculus operations through our generalized coordinates formulations, right? We also are going to solve the wave equation in generalized coordinates at the end of this lecture. So then we can separate variables and obtain the wave functions for any coordinate system that we can define, at least where the Helmholtz equation is separable. And there are 11 of them, so 11 different coordinate systems that the wave equation is separable in. And you'll understand that as we go through the lecture. Okay, so let's start out. How do you know you have waves, right? We need to understand what a wave function looks like, or a function that describes wave behavior or propagation of waves, so that we can search for the differential equation hidden in Maxwell's equations that has these types of solutions. All right? So the first thing I'm showing here is y equal to f of x, this red curve. We have an x, y graph here, or an x, y plot. We have this function y equal to f of x, which is a linear function, right? Now, we all know to translate that function along the x-axis to subtract from its argument, right? So this function here y equals to f of x minus a, f of x minus a equal to x minus a is the same function y equal to x, but translated along the x-axis by an amount a, right? Okay. Now, if we make that constant a that we subtracted from our argument of our function to translate it along the x-axis a variable, so that now this a is v times t, where t is some time coordinates, right? T is a continuous variable. As t increases, then that function will be seen to move along the x-axis, right? So this linear function now becomes dynamic, and it moves along the x-axis at a velocity given by v. So what we can say is that, okay, so let's take it one step further. If our function, instead of y equal to f of x equal to x, we have y equal to cosine of x minus vt. Then we'll have a cosine function that appears to move along the x-axis to the right, right? With time. And exactly what does that look like? Here's an example of that. Here's a cosine function, right? This is cosine. If you were to pause this, I wonder if I can pause it. I'm not sure I can. But if you were to pause it, you would see a cosine function. And all this cosine function is doing is translating to the right with time, right? But we can also see that this is wave behavior. Imagine each one of these little vectors, these green vectors, is a patron at a baseball stadium doing a wave. So they get up out of their chair, they sit down. Then the neighbor gets up out of their chair and gets down a little bit out of phase, right? So that's exactly what's happening here. This person gets up, sits down, the next person gets up, sits down, right? And you see the wave go around the stadium. So this wave appears to propagate down the x-axis. And we know that a function that has this form describes wave behavior, f of x minus vt, right? So inside of Maxwell's equations, buried somewhere, must be a differential equation which has a solution of this form, f of x minus vt, right? So let's see if we can find it. So functions of the type f of x minus vt represent waves. Of course, we have to be cognizant that you can also add to the argument, right? This whole entire argument can be repeated for functions which are translated along the negative x-axis. And in that case, we'd add to the argument, f of x plus a, right? Or cosine of x plus vt. So there are two solutions in general, one that moves to the right and one that moves to the left, right? So let's see if we can find it in Maxwell's equations. So we're going to consider source-free and lossless media, meaning that these are differential equations to describe behavior locally around a point, right? Describe the rate of change locally around some point. So we're assuming at that point that there's no charge, there's no current, and the conductivity is zero. So it's lossless and source-free media, right? Okay, so lossless and source-free media. So we're looking for a wave type solution, f of x minus vt, to Maxwell's equations. So let's see if we can find a differential equation which has that type of solution. So here's Faraday's law. If we take the curl of both sides of Faraday's law, then we have this operation on both sides. And we can recognize that the derivative, the temporal derivative, and remember the upside down triangle is nothing but spatial derivatives. So don't be scared of it. Think of it as partial by partial x. We can interchange these two derivatives, right? Or we can factor out the time derivative out of the curl operation. And what we get here is this operation here. Now, let me clear this out. This curl of H, we can use Ampere's law and replace it with partial d by partial t, right? So you get minus mu partial by partial t, and then the curl of H from here becomes partial d partial t. So we get a second derivative of the electric flux density, right? Okay. Now, so here is our differential equation we've derived. We need to do something about this curl of E. So we use our friend, the vector identity that you derived in lecture 1. We use that vector identity that we derived in lecture 1, right? We know that we're at source-free points, so divergence of D is equal to 0. And hence we can also say that the divergence of epsilon E equals to 0. And from here, we can say that the divergence of E equals to 0. What have I assumed about the medium in deriving this result?
Assume that it's both uniform and constant.
Very good, homogeneous, right? This constant, remember the upside down triangle is nothing but spatial derivatives. So if I pull this constant out of the derivative, then it must have been a constant with respect to the coordinates of which we're differentiating over. And these are spatial coordinates, x, y, and z. So epsilon must have been constant with respect to space. All right, good. So if divergence of E is 0, we know this term can go to 0. So let me clear up this. So this term goes to 0. So then we end up with this equation here. All right, great. Let's check if this is, so first off, this is a vector wave equation, right? This is a vector partial differential equation. It has a result, a function that we're searching for, a function that satisfies this differential equation is a vector valued function. And it's a partial differential equation because it involves partial derivatives and multivariate functions, right? So let's specialize the case to 1D. So we're gonna assume that the electric field is y-directed only and is a function of x only. Okay, if we do that, then this is the equation that results, right? Because the derivative with respect to y drops out, the derivative with respect to z drops out, and all of the other components, there's only a y hat component, right? Okay, very good. Let's check if this is a differential equation with our type of solution, with wave type solutions. So let's assume that EY, this function here, is cosine of x minus CT, where C is the speed of light, all right? We're searching for these types of solutions. If we plug that into the left-hand side, so the left-hand side is this, right? So if we differentiate this function twice with respect to x, what do we get? We get minus cosine, right? Very good. Oh my goodness. We get minus cosine of x minus CT. All right, let's check the right-hand side. The right-hand side is here. 1 over c squared, partial squared EY over partial t squared. We keep the 1 over c squared out. We do one derivative with respect to time first. A c comes out, a minus c, right? And we have c sine x minus CT. We differentiate again with respect to time. Another minus c comes out, and we get, that cancels the c squared, right? And we get minus cosine of x minus CT. The left hand and the right hand side match, meaning the equality is upheld, is satisfied. Therefore, this equation, so for this type of solution, which is a scalar function, not a vector function, we have a 1D scalar wave equation that we derive directly from Maxwell's equations that have wave type solutions. So Maxwell's equations, as you learned them in the beginning, are sort of these separate, they're not separate, they're laws that govern different phenomena that were, you guys read that as part of your homework, the paper on the history of Maxwell's equations. So you know how they were developed, kind of to explain different experiments and phenomena that were observed in the 1800s and 1700s, right? So from Maxwell's equations, if you rearrange them, you can derive a wave equation, which then gives rise to waves, right? Waves. Very good. Okay, so note, as we said before, you could have a plus or a minus here, right? We expect that. Why do we expect that? First off, what do you know about differential equations of order 2? How many solutions do you have to a differential equation of order 2? 2 linearly independent solutions, right? So we need 2 linearly independent solutions to fully solve the differential equation, and they're the forward traveling wave and the backward traveling wave. All right? Any questions? Yes.
Looks like you used Faraday's law and Ampere's law to get this
Yes.
derivation. So how can you be sure this also satisfies the other two laws? Is that already in there implicitly?
Very good. Very good question. Yeah, we did use it here, right? Divergence of D equal to 0. So we invoked the necessity for Gauss's electric law. However, we can also do the same exercise for deriving a wave equation in H. So we derive this in E, right? You can do the exact same thing by starting with Ampere's law here and taking the curl of both sides and substituting in Faraday's law. And you would arrive at a wave equation for the vector field H. And there you would probably use divergence of B equal to 0. In fact, you would, right? So it's a great question. Yeah, good question. Okay. All right. Okay, so now that we've derived the wave equation, we need to solve it, right? We derived the second order partial differential equation. It's a vector partial differential equation. So it's going to be difficult to solve, right? So we're going to solve it in 3 different coordinate systems and then in generalized coordinates in this lecture series. Okay, so here's a little table that I've made, or a little flow chart on how we're going to do that. So we start with Maxwell's equations in full generality. The fields are a function of space and time, right? And they're written in terms of E, B, D, and H, right? All sources appear. We're going to specialize our temporal dependence to explicitly stating it to be sinusoidal or time harmonic, right? So that means that we can take this vector field, E, as a function of X, Y, Z, and T, where T could be anything, could be pulses, could be sawtooth, whatever type of temporal dependence you want. And we're going to specialize it by explicitly stating that its temporal dependence is harmonic or sinusoidal. All right, good. If we use that, we can recast our Maxwell equations into what are called the time harmonic Maxwell equations, meaning that what is the price we paid to do that? You guys remember? What's the difference between this form of Maxwell equations and this one? One big difference. Complex, very good. So we now have complex arithmetic here, right? All of these are complex vector fields, complex valued vector fields. They have magnitude and phase, real and imaginary part. You can see that with the J's, right? Now there's a J omega. Whereas over here, these Maxwell equations are real valued vector fields. Very good. Okay. So now we have time harmonic excitations. The fields are now only functions of space. That's what we gained out of assuming this temporal dependence. We were able to factor it out and cancel it. So these are time independent. These vector fields are all functions of spatial coordinates only. And the equations involve E, D, H, and B. Okay, good. Now we're going to invoke the constitutive relations, which you learned in lecture 2, that link the intensities to the densities. So we have field intensities and we have flux densities or current densities. And they're linked to the constitutive parameters that describe media. So by having these constitutive relations, we now introduce media, because here we don't have any description of media, right? These are fields in general, but they don't describe the effects of media. We need epsilon, mu, and sigma to describe media, the response of media, right? Okay, so by using the constitutive relations, we end up with this set of Maxwell's equations. What do we notice about this set? Remember, here we have 4 unknown fields, right? We have 4 equations. We have 4 unknown fields. We need to solve it, at least for one, right? That's what we're trying to do, is get to an equation we can solve. So what happened here? E and H only, right? We use the constitutive relations to eliminate D and B and J and express them in terms of E and H. So this Maxwell equations are now only functions of E and H. So we're getting somewhere. Good. However, the differential equations that we need to solve are coupled vector differential equations. These two, for example, they're coupled vector partial differential equations, and you must solve them simultaneously. You might get scared seeing this. If I gave you this on an exam, you might be worried, how do I solve these, right? These are kind of complex looking. But if I gave you this on an exam, you would know how to solve that immediately, right? 2 equations, 2 unknowns. And you know how to solve this. This isn't intimidating. This is the exact same thing. We're going to approach it in the same way. We have 2 equations and 2 unknowns. The operations are different, right? They're not simple multiplication and divide or add and subtract. They are vector calculus operations, but they're nonetheless the same thing, right? We approach it in the same way. Okay, good. So we need to uncouple these differential equations, which is the same thing you do when you solve this system of 2 equations and 2 unknowns. You uncouple them. You solve these so that you derive an equation in terms of x only, right? Or y only. Then you can solve for x or solve for y. Then you can go back and substitute, right? So we're going to do the same thing, same strategy. Okay, so what do we do here? To derive these, we have the curl of E equals to minus J omega mu H, for example. If we take the curl of both sides, we did this on the last slide, right? We can substitute in for the curl of H from this equation, right? For this part here. And then we have an equation only in E. So we've uncoupled them, right? We did that on the last slide. If we do that, we assume source-free media, take the curl of both sides and substitute. Then we end up with this vector PDE that we derived on the last equation, on the last slide. Now, the difference between what we did on the last slide is we left Maxwell's equations in the time domain, yeah? We derived the wave equation not assuming time harmonics, all right? But the process is the exact same. Here, if you do the same thing, you end up with the del squared E plus beta squared E. And we'll understand what beta is. We'll derive this again, all right? In the next slide. So now they're uncoupled, but what's the price that we pay to uncouple them? Don't look here yet. What is the price that you paid? We've increased the order to second order, right? The Maxwell equations in this form are first order. These are first order derivatives, right? First order derivatives. First order differential equations are generally easier to solve. So here we've increased the order. So we paid the price we've uncoupled them, but we paid the price by increasing the order of the PDE. All right, so we have to solve this PDE, right? But the good news is we have one equation in one unknown, which is now solvable. Okay, good. So let's write out the vector field in terms of its components X, Y, and Z. And in rectangular coordinates only, as we understand, we can separate this vector PDE into three identical scalar PDEs, all right? They're scalar PDEs because they operate on scalar functions. Remember, this is a function of X, Y, and Z still. It's a multivariate function, but it's not a vector. It's a scalar function. And they all have the same form in rectangular coordinates only. We'll understand that more about that in this lecture, all right? So just know in rectangular coordinates, we can separate into three identical PDEs. They're scalar PDEs, so it's getting a little easier to solve now. So now we have scalar PDEs, we can start to solve these. Okay, good. All right, so we're going to use a technique called the separation of variables, which we're going to go into depth in this lecture on to solve these PDEs, right? Since they're all the same form, we can solve one and therefore imply the solutions to the others by inspection. So we'll derive these, but what results of applying the separation of variables technique is three ODEs, three independent ordinary differential equations. See, these D's are straight, they're not script. Three independent ordinary differential equations, which are all linked together in this equation called the separation equation. And that separation equation models the original PDE. So these four equations are the solution to one of these. And we're going to do all the derivations. So this is just a preview. All right? Good. Any questions? Very nice. All right. So let's derive the wave equation in time harmonics now. So we start with Maxwell's equation in source-free media. We're in time harmonic domain. We have negative j omega mu and j omega epsilon prime. And these are coupled vector PDEs. So we're going to use the same idea as the aside here, right? So the reason I put this aside is because I want you to not be intimidated by trying to solve or separate the system of it's two equations and two unknowns, right? This is two equations, and the two unknowns are now vector fields, E and H. So on the aside, you can solve a system of two equations and two unknowns, ax plus by equal to c, dx plus ey equal to f. We solve one equation for one variable and substitute it into the other, right? So to solve the first equation for x, we get this expression. And if we substitute that in for x here in the second expression, then we now have an expression completely in terms of y, and we can solve that, right? So now we have one equation in one unknown. We can solve for y. Then we go back and substitute it into this expression. We end up with an expression, or no, we can substitute into here. And we can solve for x, yeah? Okay, that you know how to do. So it's the same idea, right? So take the curl of the first equation, both sides, substitute the second. So this becomes the curl of h here from here, and multiply out these coefficients by FOILing, and you get this expression here. Very good. Now use your vector identity to change the left-hand side into minus del squared E plus the gradient of the divergence of E, and we still have the same right-hand side. And from there, we know that the media is source-free, so we can eliminate that term. And we end up with this wave equation here, all right? This which is a homogeneous wave equation for the electric field E. We can define what's called the propagation constant del squared, or gamma squared rather, equal to j omega mu sigma minus omega squared mu epsilon. If we define that propagation constant, we can write this equation in this form, where gamma in general has a real and an imaginary part. The real part we call the attenuation constant, which will become clear in the next few slides. And it has units of Neppers per meter. So I think somewhere in this lecture, I put a description of what Neppers are. So we'll look at that. And then the phase constant, which is radians per meter. All right, we'll understand what a phase constant is. Once we solve once we solve this equation, then we'll go back and in the solutions, we'll interpret what alpha and beta are. All right? Good. Any questions? Very nice. Oh, there's a question on, okay. Why is it epsilon prime? Okay, good question. So let's go back. Epsilon prime here, right? If you remember from lecture 2, we either wrote epsilon as a complex number. So we said epsilon is equal to epsilon prime minus j epsilon double prime, right? We either wrote it like that, or we had the sigma effective and epsilon prime. So we included the loss in the effective dielectric constant, or sorry, the effective conductivity. If you go back to lecture 2, you'll see exactly where this comes from. It's either j omega epsilon complex E, and then we have sigma static E, right? Which is purely the conductivity due to metal. Let me write that out for you. So it's either j omega epsilon complex E plus sigma static E, right? Where sigma is only due to the conductivity of the metal, and epsilon complex contains both the storage, epsilon prime, and the loss due to the dielectric heating loss, which is the epsilon double prime. Or you can write it in this form, where epsilon prime, this term completely accounts for the displacement current in the storage, and the losses are all embedded in sigma effective, where sigma effective contains the effects of epsilon double prime. If you go back to lecture 2, you can look back at that. So it's definitely not, there's a point to the notation, all right? Okay. Okay, so here, actually I have it on this slide. In lossless media, we have sigma effective is sigma static plus omega epsilon double prime. So sigma effective contains the epsilon double prime term, right? But in lossless media, we're going to assume that that's equal to 0. There's no losses. Sigma effective accounts for all forms of loss. Hence, the propagation constant becomes gamma squared minus omega squared mu epsilon prime, where epsilon prime does not include the losses, right? It's epsilon prime. It's the real part of the complex permittivity. So, big note, from here forward, sigma will refer to sigma effective, and epsilon will refer to epsilon prime. So from this point, we're going to use that notation, okay? Okay, so for lossless media, we define the wave number beta as omega squared of mu epsilon. We'll understand what the wave number is. We're making these definitions now, but I'll show you what they are. So the vector wave equation becomes del squared E plus beta squared E equal to 0. Why? Because gamma squared in general on the last slide was j omega mu sigma effective minus omega squared mu epsilon. All right? If sigma is equal to 0, sigma effective, then we end up with gamma squared is minus omega squared mu epsilon prime. Omega squared mu epsilon prime, right? And furthermore, for lossless media, we're going to define beta as omega squared of mu epsilon, or beta squared. Let's do beta squared. Beta squared is omega squared mu epsilon. Good. So we can write the differential equation here, but now you see this is plus and this one is a minus. And the reason is we have omega gamma squared equal to minus omega squared mu epsilon, but here we're saying that beta is equal to plus omega squared mu epsilon. All right, so the mathematics works out. Okay, good. All right, so we have this wave equation here, which is the most common form that you'll see. In rectangular coordinates only, we have del squared equal to, okay, so I want to ask you guys, why do you think this holds? And I'll give you a hint, you did it in your homework. In homework number 1, I asked you to look at the derivatives of various unit vectors, right? So why is it that only in rectangular coordinates this identity holds? Let's think about it in general. If you have del squared of E, right? So this is del squared E. So this is del squared into E x, x hat, E y, y hat, E z, z hat, right? Okay, let's do the first term, which is partial squared x squared into E x, x hat, right? That's the first term. What do we have to do here? What's the next step in that line of mathematics?
X times X hat plus.
Very good. Product rule, right? So this is partial squared EX with respect to x squared, x hat, plus partial squared x hat EX, right? So the derivative of the unit vector is there. But we know that in rectangular coordinates, which is this unique coordinate system, because each of the unit vectors, remember, what defines a vector? It has two properties. What are they? Direction and magnitude. Now, if either of those change, then the vector is not equal. If those are equal for any other vector, then those vectors are equal, right? So this vector here and this vector at the origin, even though they're at two different locations in space, are equal because they're the same magnitude and direction. But this vector here and this vector have different directions, same magnitude, they're different vectors, right? In the rectangular coordinate system, x hat, so what are we differentiating with respect to? X, right? So does x hat change its magnitude or direction at all points of x as I change x? It does not, right? It stays the same direction, x hat, and the same length for all points in space. Therefore, it's a constant unit vector. Therefore, its derivative is 0. So this term goes to 0. And what it looks like is that this second derivative distributes into each of the components, right? Like this, if you did all the terms. Now, we know in cylindrical coordinates, if I didn't use Cartesian here, if I said, you know, partial squared, partial rho squared, and then we'd have, you know, rho hat E rho. Okay, that's a bad example because that one, but the phi, right? If we did phi, we did the phi, rho hat changes with respect to phi, right? So you would see that that doesn't hold in other coordinate systems. Okay, good. So the wave equation splits into 3 identical equations, these 3 equations here, right? Good. Okay, one thing we notice about these is we have del squared EX, these are scalar PDEs now, del squared EX plus beta squared EX equal to 0. This looks exactly like, if you write it here in this form, exactly like AX equal to lambda X. Have you guys taken linear algebra? If you haven't, you should. It's a very good course. It's useful for us, right? And most of the things that we do, Maxwell equations are linear, right? So all of the principles that you would use in that course can also be applied to electromagnetics. Especially, so here's one example, right? Del squared EX equal to negative beta EX. Ax equal to lambda x is called an eigenvalue equation. A is an operator, it's a matrix, that a linear transformation that operates on a vector x, and it produces a new vector x in the same direction, same vector, scaled by some scalar value lambda. We call solutions to this type of equation eigenvectors, and the scale factor is called an eigenvalue. So if you've seen this before, then this might light up some light bulbs for you. This is the same exact equation. So what we call these functions here they can be called eigenfunctions of this wave equation. And the scale factor beta can be considered an eigenvalue. So if you've seen that before, that might help. Okay, these are solutions. So E, X, Y, and Z are called eigenfunctions. The eigenvalues are beta. All right, so here's an aside over here that maybe we'll come back to at some point. I think I'm going to skip it for now, but it's how to solve the inhomogeneous wave equation using modal expansion. All right, but we're going to solve the inhomogeneous wave equation using what's called a Green's function and convolution. So we'll come back to this if we need it, but it's something interesting. If you're interested, dig deep into it, then you can read this. Read this on your own. It'll be interesting for you. Okay, good. The reason why it's there is because we're using eigenfunctions in order to solve the inhomogeneous wave equation. So it links back to these, right? You can, if you know the eigenfunctions of a differential equation, you can solve an inhomogeneous version of that using expanding both sides of the equation in terms of those eigenfunctions. All right, good. So let's move on. So let's solve this differential equation now. We have this differential equation. We can solve one of them, Ex, for example, and we get the other two by similarity. So let's solve this. The del squared expands into this form here, all three partial derivatives, second order. Then we're operating on Ex here, and we have beta squared Ex that remains, right? Okay. These are partial derivatives since since the function they act on is a multivariate function, of course, right? Del squared is partial derivatives. Ex can be written as a product of single. Okay, so here's the idea. We're going to assume, we're going to make an assumption that our function Ex of x, y, and z can be written as a product of three single variable functions, a separable form. So here's the key step. Let's assume that E can be written in this way, as a product of three functions of a single variable. What's the strategy? Why do we want to do that? Because then we can change these partial derivatives into ordinary derivatives. That's going to be the result. But it's not guaranteed that E can be written in this form. So what we're going to do is assume that we can do that and plug it into the equation and reduce it into something that may or may not be solvable depending on whether this assumption holds. All right? Good. So for Ex, now we're going to plug in F, G, and H in both here and here, right? Now what we're going to do is distribute these derivatives. So we have partial by partial x squared into FGH, partial by partial y squared into FGH, partial by partial z squared into FGH. We're going to move this term to the other side. It becomes negative. Good. Now, why did we write E in terms of F, G, and H as a single variable, product of single variable functions? Because of this exact step here. From here, we can factor out, this derivative is only a function of x. We can factor out G and H from this function here, and we end up with G and H d to dx squared f of x. So the partial derivatives have now become ordinary derivatives. And that was the key motivation to this step, right? These partial derivatives become ordinary derivatives when we have a separable function that this partial derivative operates on, all right? We can do that for all three terms, and we end up with this equation. These are all ordinary derivatives now. Any questions? Good. Okay, let's continue. So I've repeated the differential equation here. Now we're going to divide through by f, g, and h. And in doing so, we end up with this equation of the form here. 1 over f d2 f dx squared. This term is only a function of x now, which is good. 1 over g d2g dy squared. This term is only a function of y. And 1 over h d2h dz squared is only a function of z, right? So we've separated this differential equation, it's a partial differential equation, into three terms which depend only on a single variable, and all of those must equal to a constant at the end. So how can you add f of x, g of y, h of z, three functions which depend on different variables together to obtain a constant only? The only way you can do that is if each of these three terms are themselves equal to a constant. Why? If this one ended up being some function of x, if this term, I differentiated whatever f of x is, and I ended up with, instead of a constant, a function of x, right? So 2x or x squared or whatever, right? Then there's no other term that's a function of x that I can add to that term to remove that x and end up with a constant at the end, right? So the only way this holds is if these three terms are constants themselves, because they're functions of different variables, each of those terms, right? Okay, so knowing that, let's set this term equal to a constant. You'll see the motivation of why we chose negative beta x squared for that constant, but it could be anything, right? Any constant value we want. We're going to call it negative beta x squared. This one we're going to call negative beta y squared. And this one we're going to call negative beta z squared. All right. So that means that this whole term we can replace with beta x. This whole term, beta y. This whole term, negative beta z squared. And that equals to beta squared. That's this equation here. So the PDE has reduced to this equation. Beta x squared plus beta y squared plus beta z squared equal to beta squared. Right? Of course, to find what beta x, beta y, and beta z are, you have to solve these equations here, right? You have to solve these. So even though it's, looks simple, it's not, right? Okay, good. So there are three ODEs. These are independent ordinary differential equations. You can solve these independently and know that their solutions must be linked together by this equation in the end, right? Very nice. All right. So we have three ODEs that are linked by the separation equation. This equation is called the separation equation. Very important equation, right? We'll understand this in depth later, but it restricts your wave type solutions in different directions. They'll have to be linked somehow. So we'll understand that, okay? Very nice. Any questions so far? All right. Very good. Yeah, this is fun.
I have a question actually.
Yeah.
So what does it mean for that function to equal to a constant? That's just a restriction on the solution. So whatever f of x, yeah.
Yeah.
For example, what does that mean? That's equal to a constant?
So, okay, it looks like, so whatever, okay, let me rewrite that equation in this form, right? So let me say d2f of x dx squared plus beta x squared f of x equals to 0. Now it's a differential equation, right? Same equation. Setting it equal to a constant allowed us to write this form up there. And all that function says, or all that differential equation says is, what function can I differentiate twice, add it back to itself and get 0? There's cosine, there's sine, and exponential, right? So we're going to do that on the next slide. Okay. Okay, so since they're all of the same form, we can solve one and infer the solution to the other, right? So let's solve this one. Exactly what I just did. We can rewrite this like this, right? So what functions are equal to their own second derivative scaled by a constant? We have sine, cosine, and exponential, right? Sine, cosine, exponential. If you differentiate sine of beta x twice with respect to x, you get minus a beta x squared sine of beta x. You get the same function back, a times sine. You get a times sine back, scaled by beta x squared, which is exactly what that differential equation says, right? You should differentiate twice. You should get the same function back, scaled by negative beta x squared. So here's negative beta x squared, and the original function was a sine, so here's a and sine, right? So you get the same thing back. Good. Okay, you can do the same thing for cosine. And you can also do exponential functions. So these two we'll see soon that they represent standing waves, which we'll understand what standing waves are. We'll derive the properties of standing waves. But no, for now, sine and cosine are standing waves, and traveling waves are exponential types. So we've done it. We've solved Maxwell's equations for wave type solutions. We've solved the wave equation. These are the solutions to the wave equation, f of x. So remember, we assumed that Ex of x, y, and z could be written as f of x, g of y, h of z, right? Well, f of x, we've just found, is a e to the plus or minus j beta xx for a traveling wave solution. All right. We can find g and h in a similar way because those differential equations are the exact same form. So they're also exponentials. So Ex, f, g, and h, this is the solution for Ex, the x component of the electric field of the wave equation. But we had three constants, beta x, beta y, and beta z. What do we know about these three constants? Well, in this case, it's a lossless. So whenever you see beta, it's a lossless medium. So it's a real value. These are complex functions though, right? We know, yes.
How are they traveling waves if we don't have time?
Excellent question. Yeah. So good question. Remember, when we had, so remember this is e to the plus or minus j beta x, right? Remember, one of the first things we did was we assumed time harmonics, right? And in time harmonics, we take that function, we multiply by e to the j omega t, and then take the real part. All right? So let's do that. So the real part of e to the, let's say, j beta xx, and then we multiply by e to the j omega t to get back to the time domain, right? What does this become? The real part of e to the j beta. Okay, so let's put a minus here. It doesn't matter, right? One wave goes one way, one wave goes the other way. E to the j, what the? E to the j omega t minus beta xx, right? What is the real part of the exponential? It's cosine, right? Because exponential equals cosine plus j sine. So this becomes cosine of omega t minus beta xx. And you can pull out a minus sign, and what do you get? Cosine of x minus vt, which is the wave cosine that moves to the right, right? Yeah, for sure. So remember, whenever you solve these Maxwell equations, you'll get this complex function, right? You'll get that part of it. To get to the actual solution that you would measure in a lab or whatever, you'd have to multiply by e to the j omega t and take the real part. But typically, when you solve these problems, and you publish papers and all of that, you can stop here because this step is implied, right? If you say in your paper you're working, you don't even have to say that you're working in time harmonics. What you do want to say is that that your time convention is e to the j omega t, somewhere in the introduction. Because sometimes people choose e to the minus I omega t, and that conjugates everything. So just say the time convention of e to the j omega t is assumed and suppressed throughout. And then your solution to your paper is this complex function e of x, y, and z, right? Okay. Unless, of course, you're working with some other time variation than harmonics. Okay, good. So, yeah, these represent traveling waves. We should get used to that. If we see an exponential e to the minus j beta xx, we should think of them as traveling cosines, right? Based on what we just saw, right? Okay, so here's Ex. Then we can go back. We know that all the PDEs, the scalar PDEs that we derive from the vector PDE, remember? So these are all the same form. We solve one of these, we can get these two by inspection. We did that. But we also, here, where we had E like that as a vector, we were able to write it as Ex, x hat plus Ey, y hat plus Ez, z hat. we derived these three equations, we solved this one, but these two are exactly the same. So we've also solved those two, right? That's why we were able to write down immediately what G and H are. It's the same thing as what F was. And then we're able to also write what the vector field E is, because we solve for EX from here, but we know EY and EZ immediately by similarity. Yeah. So it's a bunch of exponentials.
Should be A cubed, right?
Okay, yeah, you can call it A cubed, or you can just call it A again. Some unknown constant, right? You just lump them all together into a new A. But good point. Okay, good. So there are different ways to classify these solutions, as we said. If they're exponentials, so these are the solutions to, these are the eigenfunctions, the solutions to the homogeneous wave equation. They're traveling waves at their exponentials, right? E to the minus means that it's traveling in the plus x direction, and e to the plus means traveling in the minus x direction. And you can easily verify that by taking the real part, multiply by e to j omega t, and then seeing which way it translates, right? Standing waves, as I mentioned, are cosine and sine. There are what are called evanescent waves, which decay. They don't propagate, they decay, right? Because there's loss in the medium, and those are e to the minus alpha x. Notice there's no j in these. It's not e to the j something. E to the j implies oscillation because it's cosine and sine. But e to the minus alpha is a real valued function. It doesn't have the cosine plus j sine Euler identity. It's just a decaying exponential. Then you can have attenuating traveling waves by combining those two. And then there's some attenuating standing waves by using hyperbolic sine and cosine. All right? And we'll get used to using all these different forms throughout this course. Very good. So let's do an example so we can kind of get a feeling for how to choose these wave functions in the right way. Let's write the solution for EX for the fields within a rectangular waveguide. So I'm aware that you haven't studied rectangular waveguides yet. We'll do that, as a matter of fact, in the next course. But here I'm just going to tell you that there's a rectangular pipe. Remember how I told you before, if I talk to you guys, if I want to talk to a specific person, then as I talk to that person, I'm also spreading the energy of my voice in all directions. So it's kind of inefficient. If I wanted to direct all of my energy to a single person, then I could use like a wrapping paper tube or like a super long toilet paper tube and talk into it. And it would guide the acoustic wave directly to the person, right? So it's like a hollow pipe that guides the energy of my voice to some person. This is the same thing. So that hollow pipe, what it does, it provides boundary conditions that the wave has to satisfy from all the way through its path. This does the same thing. It's a rectangular hollow pipe, and it confines the electromagnetic energy because since it's metallic, the energy cannot penetrate it, right? E tangential equals to 0. It reflects off the sides, right? Inside of here. So if I put some source in here, the energy must travel along the pipe. So there's a specific form for the electric field within that pipe, and it is here. Okay, so we're gonna figure that out in general, right? So we're gonna derive that. So we start with our solution F, G, and H. We're gonna assume the electric field within this rectangular waveguide has only an X component. We're gonna write it in this form. So we need F, G, and H. Remember, F is a function of X only, G is a function of Y only, H is a function of Z only. We start with F, which is cosine of beta XX, sine of beta XX. So we don't know if it's sine or cosine yet. We're going to include them both to be general. Remember, f of x is a solution to a second order differential equation. So it has two independent solutions. So those two independent solutions are cosine and sine. We'll put some arbitrary constants there first. Then why are we choosing that? Because we know the waves traveling in this x direction, right? So they're traveling in this direction. We know that they're going to encounter a metallic wall and reflect. Then they're going to encounter another metallic wall and reflect. So in the x direction, they can't travel in unbounded medium. They have to stand. They'll end up being standing waves within the pipe, right? Same thing in the y direction. They have to be standing waves in the y direction because they're not free to travel. But in the z direction, which is down the pipe, there's no wall to reflect on. It's an infinite hollow pipe. So we can assume that they're traveling waves. All right. So let's apply the boundary conditions to determine the various wave numbers, beta x, beta y, and beta z, and the coefficients c, d, and a, and b. So the boundary condition, for example, Remember, what is the boundary condition on perfect electric conductor? Tangential E must go to 0, right? You got to remember the boundary conditions. It's the most, if you remember nothing else but boundary conditions from this whole course, that will help you. So tangential E goes to 0 on PEC. We have EX, right? So X is directed like this. The electric field is in the X direction. Tangential has to go to 0. So at Y equals to 0, EX better be equal to 0. And at Y equal to B, X must be 0, right? So at Y equals to 0 and B, EX must equal to 0 because it's tangential to metal. Thus, okay, so this whole function, EX, has to go to 0 when Y is equal to 0. So we're looking at this because it's the Y dependence. When Y equals to 0, this term already goes to 0, right? So that's okay. But this term does not. When Y goes to 0, cosine is equal to 1. So this coefficient must be, C2 has to be 0 in order to force EX to be 0 at Y equals to 0, right? Everybody see that? Very good. So C2 must be 0. All right. What about when Y is equal to B? When Y is equal to B, we know this turns out already, right? Because C2 is 0. So now we're left with sine of beta Y. When Y is equal to B, then when is the sine function equal to 0? When does sine of X go to 0? N pi, right? So N pi must equal to beta Y times B. This beta Y, whatever beta Y times B, right? Beta Y times B has to equal to N pi in order to force this term to go to 0, right? Everybody understand that? Very nice. So if you solve this, then you get this. The eigenvalue beta Y must be N pi over B. All right, so you can find the remaining wave numbers and coefficients in a similar manner. So that's like a little exercise or a glimpse on how to construct, how to write the functions for different geometries, problems. Yeah? Okay, good. Any questions on that? All right, now I'm going to get into a topic which is super important for you guys to understand. It's super useful. It's used to solve, once you're able to harness this concept, then you can solve problems and look like you really understand what you're doing, right? This is a very interesting topic. So first off, what I want to draw your attention to is these solutions to Maxwell's equations ended up being sines and cosines and exponentials. Why do you think that is? So try to make the connection. So we ended up with sines and cosines and exponentials. What kind of functions are these? A periodic, right? They're sinusoids, they're periodic, very good. They're time harmonic, right? The reason why we ended up with these solutions is because we solved Maxwell's equations in the time harmonic form. We assumed that the temporal variation was sinusoidal. And we know Maxwell's equations links the time derivatives to the spatial derivatives, right? The wave equation. So, and it's linear. So we expect the spatial variation to also contain some kind of harmonic behavior, right? Assume single frequency excitation. If I have a source here in this room, like you turn on the light switch, the whole room fills up with light, right? But before there's a transient time when that light bulb starts to fill the room, but the rest of it is dark and it reflects off of all these objects and the whole room comes into a steady state, but it's filled with electric field now. If I turn on this source, it starts to oscillate, but it's oscillating sinusoidally by our assumption, e to the j omega t. Sinusoidal oscillation, right? The temporal time dependence of the source. Since Maxwell's equations are linear, every other vector in the vector field, the electric field, which results from this sinusoidal source, must also vary sinusoidally. It has to vary sinusoidally because of linearity. So that means that because we chose time harmonic, time dependence, sinusoidal, these wave functions also end up being sinusoidal. All right, that's cool, but that brings us so much more power than you can imagine. Because what do we know about superpositions of functions or weighted combinations of these types of functions?
It's a solution.
It is. So, okay, so sometimes I ask like a vague question because I know what I'm looking for. And you guys probably, I'm trying to like ask a question to direct you there. So if I add up a bunch of sines or cosines with different coefficients, what does that remind you of?
Fourier transform.
Very good. Fourier series, Fourier transform. All of the power of Fourier theories of Fourier transforms and Fourier series, that's all tools for us in electromagnetic theory. Because we chose e to the j omega t time convention, because we're solving time harmonic Maxwell's equations, because Maxwell's equations are linear. So we can add up a weighted combination of, remember when we looked at solving the second order differential equation, we found that we can add a weighted superpositions of solution, and that's also a solution. Or maybe we haven't done that yet. I think I might have included that in a later slide. But you can add up as many of these terms as you want, sine of beta xx with different coefficients, and that's still a solution to the differential equation that we used to derive that. So we can add up, we can use all of the theories of Fourier series and Fourier transforms in electromagnetic theory. And that's going to become super useful and super handy. All right? Because we're working in time harmonics. Here's one such example of that. This is called the plane wave expansion and the plane wave spectrum. So if you've taken a class on Fourier series or Fourier transforms, this will be really clear. And it will really turn on some lights for you. So the plane wave spectrum representation, it builds up. So remember, we haven't defined this yet, but these are called plane waves. These traveling waves are plane waves, right? Because they're a function of x only, for example. So it's like cosine of beta x minus omega t, right? Beta xx. So it's only a function of x, right? So at, say x-axis is this way. So at this x, it's not a function of y or z. So if x-axis is that way, then x is varying that way, then at each cross section of the x-axis, there's a y and z, right? The yz plane. But the electric field is not a function of y or z in that plane. So it's constant everywhere in that infinite plane. And then the next plane over, a little bit further down the x-axis, if I take another yz plane slice, the electric field is also constant in that plane. So that's why it's called a plane wave, because the wave fronts take the form of planes because it's only a function of x. We'll get to that later. That's a preview. In the next lecture, we're going to study plane waves. Anyway, so these functions, you can also call them plane waves. So this is a plane wave spectrum representation. The plane wave spectrum representation builds up a single frequency propagating wave, E of x, y, and z, as a linear combination of plane waves. So look at this, e to the minus jkxx plus kyy plus kzz. Now k and beta are synonymous. So if you see beta or k, think of them as the same. Here, we had the same thing. You can write this exactly that way by combining them all into one exponential. All right, so we have a linear combination of plane waves. I can take, with different kx, ky, and kz, and a different coefficient a, for example, I can add up a bunch of plane waves in different directions with different amplitudes, and I can synthesize any function I want. Just like I can take a bunch of sines and sines and cosines with different coefficients and different omegas, and I can add them together to synthesize any temporal function that I want in Fourier series, right? So if I have any temporal function, a sawtooth, a rectangular function in time from linear systems, we know that we can expand that temporal function into a series of sine and cosines, Fourier series. Or conversely, I can add up a bunch of sines and cosines, and they will synthesize that triangular wave or whatever, right? But here we're talking about space, not time. So I can add up a bunch of plane waves traveling in different directions with different amplitudes and synthesize any electromagnetic field that I want, EX, any shape, right? So you might have thought, okay, when solving the wave equation, we solve this wave equation, right? Are we restricted to only these types of functions? There's only every electromagnetic field. That light that turned on in the room and filled this whole room with light, There's an electric field in this room right now, right? It is definitely not a plane wave, right? And it is definitely not, doesn't have planar wavefronts. It's some kind of jumbled mess, right? But by solving this wave equation, we think that we're restricted only to plane wave solutions. That's all we have, right? But how does the plane wave solution describe what's in this room? Well, it's through this concept here. You can add a bunch of different plane waves with different amplitudes traveling in different directions and make any field you want. It's exactly the same as Fourier series or Fourier transform as well. So the only assumption is that the field must satisfy the wave equation, which becomes a three-dimensional Helmholtz equation. We had derived this and we solved this for our wave functions that look like this. They're plane waves, right? Okay, good. So, okay, how are we going to introduce this? So let's assume that the electric field, which is a solution to this wave equation, can be written in this form. We have this function in the front. It has a squiggle on top. The tilde function or the tilde accent here is what we're going to use to denote spectral quantities. All right, you don't know what that is yet, but assume it's some function that I can plug in a kx and a ky, the wave numbers in x and y direction, and evaluate it at some point z in space, and it will give me a complex number, right? It's a scalar valued function, it's not a vector valued function. It gives me a complex number if I plug in kx, ky, and z. All right? Okay. And then we have traveling wave in x, traveling wave in y. So we know this electric field here, let's say at z equals to 0, for example, then this is also 0. Then at z equals to 0 is some cross section, right? At z equals to 0 is the xy plane. So this whole room is filled with electric field everywhere, 3 dimensions. Z is up, xy is the plane of the ground. If I evaluate what the slice of this 3-dimensional electric field looks like along the plane of the ground, then I can say at z equal to 0, E in the plane z equal to 0 as a function of x and y now, I can synthesize that, or I can describe it as an expansion of a bunch of plane waves traveling in the x direction, traveling in the y direction, and having different amplitudes, which are given by this function here. The amplitude and the phase, it's a complex number. All right, what am I doing? Now I have a 2-dimensional function, right? Let's say it's 1D, for example, only in the x direction. So I only have some electric field that's in the x direction, and I want to describe that in terms of a Fourier series, right? So I'd have to add a bunch of sinusoids that are x-directed with different amplitudes, right? So these are the sinusoids that are x-directed. Different wave numbers. Remember, in Fourier series, you have e to the j omega or cosine of omega t, omega nt or n omega t, right? So you have different omegas. Here you have different k's. And for each k, I have a different complex amplitude from this function. All right, it'll become clear later, right? So let's take our assumed solution, which is in terms of an expansion of plane waves in the x and y directions with different amplitudes given by this function here, plug it into the wave equation. We do that, right? We're there. Now, the key to this expansion, why do we choose this expansion, is I can do the spatial derivatives with respect to x and y now. And what do I get? If I differentiate with respect to x, what do I get? I get minus kx comes down. Or sorry, not kx. With respect to x, right? Here, with respect to x. Here's with respect to x. This function is a function of kx. So it's constant with respect to x. And we differentiate with respect to x, then minus kx comes down. Differentiate with respect to y, minus ky comes down. We still have the k here, and then the z derivative remains, right? Okay, good. So now we know that kx squared plus ky squared plus kz squared has to equal to k squared, which is omega squared mu epsilon, right? That came from our PDE solution. It was a separation equation, right? We always have to satisfy the separation equation. So we have k squared minus kx minus ky. What is that? K minus kx minus ky. Well, that's kz. So we can then call that kz. And we have partial by partial z plus kz into this function now because we can divide through by the exponentials because it's equal to 0 on the right. So what do we have now? We have a 1D differential equation, right? Only in terms of z. All right. What is the solution to that? Well, some function e here, if you differentiate it twice and add it back to itself scaled, you get 0. Well, that's the exponential function, right? Good. So this is the solution to that differential equation. These are complex constants as a function of kx and ky. And if I multiply each of these, if I multiply a given plane wave in the z direction with a given wave number kz, from kz, of course, from kz, I can find kx and ky because I know k, because I know the frequency and the medium properties. Then I can find the amplitude that's associated with that plane wave. And I can do that for a whole bunch of plane waves, different kz's, and I can expand the electric field in that way. So the solution then, we can write kz like this, right? Because kz squared is equal to negative kx squared minus ky squared plus k squared, right? Okay. Now, what do we note from this? This is a wave traveling in the z direction, right? We want the wave to be propagating. They're propagating in evanescent waves, all right? So first off, look at this right here. This is a square root sign, right? If we want this thing to be a traveling wave, then we need e to the minus j something, right? That's a traveling wave. Now, the only way that happens is if this quantity in the square root is negative, right? Because then a j comes out of the square root, right? So if this quantity here, if kx squared plus ky squared is less than k squared, then a j comes out, right? And this becomes a traveling wave. Kx squared plus ky squared is less than k squared, then this stays. There's a j missing somewhere, right? Unless I pull the negative sign out of this guy. Yeah, so, okay, it's correct. I pulled the negative sign out. I rearranged these three terms in this expression, right? These two aren't the same. They're related by a minus sign. Okay, anyway, then that becomes e to the j, right? So j comes out. Now, if on the other hand, that this quantity remains real valued or not, real valued, then you'll just have e to the minus some constant into z. So e to the minus alpha z with no j. That's just a decaying function, right? It does not propagate. So these are functions of traveling in the z direction. So there's a bunch of sinusoidal variations on the floor, right? Of different frequencies. There's one that has one wavelength from here to the wall. There's one that has two wavelengths from here to the wall. There's one that varies very fast. It's traveling in the x direction, sinusoid, but its beta is very high. It's a large number, so it varies very fast. And there's ones that are going this way too. So the whole floor is covered in exponentials that are going x and y with different wave numbers. Now, some of those waves that are traveling, it has a wave number along the floor. If that wave number is sufficiently small enough, then that wave will also have a component which is leaving the surface in the z direction. So that variation e to the j kxx will be associated with a wave that also has e to the j kzz. So that is a traveling wave, right? There are some that are varying too fast in the plane. So very rapidly in the plane, and therefore the kx is so high that there's not enough k to go around, is how I always say this. So let me try to explain this. This is an important concept. We have kx squared plus ky squared plus kz squared equal to k squared equal to omega squared mu epsilon. Omega squared mu epsilon is given to us by the source frequency and the properties of the medium. So those are known. That's a constant value on the right-hand side. So that's the amount of k that we have to distribute through our three axes, all right? So let's say that kx is way fast, right? There's some function in my expansion of my electric field in the plane of the ground where I have exponential Fourier series, for example. You keep adding more and more terms, right? So some of them have a really high frequency. In this case, they're high spatial frequency. So as you go from here along the floor in the x direction, it starts very, very, very fast. If I used up all of my K that I got from the source in the medium in Kx, then I will have none left over for Kz. So that wave will be trapped to the surface. It won't leave the surface and travel. So that means that it's an evanescent wave. It's trapped to the surface. You need those though, because let's say that there's some sharp discontinuity in the electric field in the floor that it's trying to describe, like a sharp corner. Then you need a whole bunch of high frequency waves to synthesize that sharp corner, if you remember from Fourier series. So you need the evanescent waves to describe the field locally on the plane. But if you leave the surface of that plane by any distance, say half a wavelength or so, then all of that fine feature detail is lost, because those high frequency waves on the surface of the ground can't leave the surface. So if that's called the diffraction limit. So if I'm observing something, if I illuminate something with a microscope and it has fine features, then there's a bunch of high frequency waves, light waves that are at the plane of the object, but they can't leave the object and go to the eyepiece, to the eye. So you only get the traveling waves, which have low frequencies in the plane of the object, right? So you can plot that in this XY plane here. This relationship's here. You can plot in a plane like this. So this is called the propagating spectrum when Kx and Ky are small enough that the low enough frequency variation in the plane XY such that that information can leave the surface. It can travel away, right? But outside of that, Kx and Ky, remember this direction Kx is increasing, this direction Ky is increasing. Outside of this radius K circle, the Kx plus Ky squared is too large to have a imaginary Kz, a traveling wave in Z. Okay, so think about that a little. We're gonna come back to this next lecture. But the more you take time to understand this, the more powerful you'll be as an engineer solving problems. This is a very useful concept. And if you've taken a course in Fourier series, Fourier transform, this is going to make a bunch of connections that'll start making you really happy. All right? All right, so I will see you guys Thursday. There's office hours today, so you can come by my office in half an hour, I think, or 15 minutes or so. Come by for office hours if you have questions on your homeworks. And I will see you guys on Thursday. All right. How's it going? Sure.
This, the last concept,
Uh-huh.
was just about planes, am I right?
Yeah, plane wave expansion.
And this like first step. You assume that we have plane wave x in one direction, and then you add this direction too, and then to the next step.
Yeah, so you take any function, So say you have like a 3D function of all sorts of, yeah, a 3D function. I'm trying to give a temporal analog that you see in the Fourier series and stuff. But yeah, in this case, we have 3D vector field, right?
Yes.
We're gonna expand a section of that vector field in that spot in terms of angle expansion close to.